his talk in a session that's one talk behind. So Morello Cerise is some ongoing work. It's incomplete. It is capture some sort of formal encapsulation property for whole architecture Morello in a theorem prover. So the state that we already have, some formal properties that are Morello from the work that Thomas just described. Is we capture whole architecture constraints, but it is difficult to see how you can use them to prove correct a program that depends on encapsulation for its correctness. We'd like to be able to do that. So can we do a little bit better? And we expect that we can, specifically because of the Cerise work from Arnold and Georges and several other authors, mostly Barhus, which formalizes sort of a secure calling convention for a significantly simplified capability machine that does let you do something like this. I should mention up front that Cerise comes in a bunch of different flavors, and we build on only the simplest of them. So we don't handle any kind of stack protection for the time being. We don't use any sort of exotic capabilities that don't exist on Morello. And so the idea with Cerise is that it provides you with a program logic. You use that program logic to prove locally sort of some chunk of known code that you've written. And Cerise then provides you with a theorem. As long as you set the state up correctly, you can compose your known code with arbitrary unknown code, potentially even adversarial code, and the invariants you have proven that your code preserves locally are preserved globally, even in the context of an adversary trying to win them. Very bottom line. So just fractionally more formally, but obviously nowhere near the full statement, if you set up your domain transition boundaries with the correct forms of protection, your locally correct invariants remain true even when interacting with adversarial code. To give a sort of slightly more concrete idea of the kind of thing you might be able to prove with this, imagine some simple accumulator like this. We start with an accumulator at 0. We provide a closure that lets you increment it. In a memory-safe language, we could prove a property that this accumulator only increases monotonically. But in an assembly context, this is just obviously not true in general. If we link with an adversary, they could guess the address of the accumulator and manipulate it in arbitrary ways. What we'd like to be able to prove is that on Morello, or any capability machine, you can set things up correctly such that the accumulator does only increase monotonically, but the adversary can't interact with this accumulator. And Cerise lets you do this. So why can't we just take the Cerise work has already been done, why can't we just do it again for Morello, for a similar technique? And this is mostly a problem of scale. The Cerise semantics is about 1 page of A4, at least a version of it is. A version of it I found while writing this talk is 700-ish lines of POCL, the operational semantics. Compared to Morello, 1,000 pages of prose specification. When we take the formal SAIL model and compile it into POCL, it's more than 100,000 lines long. So the manual approach that Cerise used is completely intractable here. Even if we had the time, we actually just can't load the semantics into POCL. If you try and execute it, POCL immediately crashes. We do have there are a handful of other problems. The biggest of those is the lossy capability compression. Cerise, at least the versions that I'm familiar with, don't handle capability compression. But Morello does do capability compression. That's annoying, both because it's quite a complicated function that we'd have to reason about, and also because it's lossy, so you can't, not all conceptually sort of reasonable capabilities are actually representable on Morello. This adds another more annoying branches to your proof that you have to deal with manually. We also, unlike the simplest forms of Cerise, we can't opt out of dealing with certain kinds of indirect capability, and we have to at least briefly mention the concept of virtual memory, even though we largely opt out of reasoning about it. So we sort of have this 2 points on the spectrum. We have Cerise deals with very simple architecture, but you get a very, very nice property. And we have the T-cherry properties, which are a name that I think has never been widely disseminated for Thomas's work, which deal with full-scale Morello, but you get a much weaker property. And the question, of course, is, can we have both? Well, to think about how we get there, let's start with sort of what T-cherry actually gives us a little bit more concretely. So T-cherry, as Thomas mentioned relatively briefly, is a collection of properties that are proven in Isabelle. They strongly contain whole architecture behaviors. They put quite a nice envelope on what an arbitrary instruction can do. Properties, this is an example of one of the properties stated very informally. If an instruction writes a capability to a register, it must be derivable from the capabilities that have been read by that instruction so far. then we get sort of two-ish things from tcherry. One is a not super formally useful, but very satisfying property that these are all properties that if you look at them intuitively, a capability architecture should satisfy. So it would be disappointing if Morello didn't, and it's good that we can see that it does. But it's not immediately obvious that you can use them in a larger formal proof nicely. If you compose them all together, you get one quite nice property, which is this sort of domain separation property that says if you have a bunch of non-interacting domains, and you set them up to non-interact quite carefully, you can reason about them separately. But if they interact, this property doesn't work, because tcherry only reasons up to domain transitions. So if we want to do sort of if we have interaction and we want to reason about the actual behavior of some concrete code, not just an upper envelope on do bad capability things happen, tcherry sort of runs out of steam. So what we're missing is a way to reason about known code on these large architectures, and we have an approach for that already. So Laris is a piece of work done by Michael Samler and myself a couple of years ago. It's a collection of tooling to automatically simplify architecture specifications for if you're trying to reason about a particular concrete program. The general idea is that we use symbolic evaluation and a SMT solver to throw away most of the specification that you don't care about for the particular program you're trying to reason about. And you get, Laris provides sort of relatively nice to use Iris program logic for reasoning about that code post-simplification. The problem with using Laris for reasoning about this sort of unknown code adversary scenario is that Laris is almost completely useless in the presence of unknown code. All of this simplification is powered by knowing the set of opcodes that might be executed, and an adversary can execute any opcode they like, so Laris falls apart. The solution is, and the proof strategy that we are working on at the moment, is we use both of them at the same time. So generally, you can sort of switch back and forth. Am I reasoning about known code or unknown code? You use the Laris program logic to reason about your known code that you've written, and you bound the sort of how much can the unknown code misbehave using tcherry. Sounds very straightforward. We've had to do quite a lot of work to be able to put these two semantics in the same language to be able to get the right properties in the right places. But once we've done that, the overall proof strategy is very similar to Cerise itself. You have a program logic for reasoning about your known code, and you have a sort of general theorem bounding the misbehavior of unknown code. So where are we at the moment in this? As I said, it's work in progress. We've done the work to adapt the Laris semantics for dealing with this, all the sort of differences that we need. Some of making it handle the capability machine, so tags, and helper functions to deal with compression, because Laris tended to blow up in the presence of those. And more importantly, we can now have a Laris with unknown code whose behavior is constrained by some arbitrary predicate. And we've used that modified Laris to verify the behavior of some of the instructions in our working example, which is a variant of the accumulator that I showed earlier. We have translated the tcherry property statements into Coq. We're not intending to prove them. They've been proven in Isabelle, and that's good enough for us. The remaining work is to finish proving out the example that we've got and show in the correct program logic form the tcherry properties are equivalent to the safety property that we need. And that work is ongoing at the moment. That's about where we are at the moment. And thank you.
We are so efficient. Questions? Quick, comma.
Are you concerned with operating systems that sit below this as well? So will your eventual end goal include being able to deal with exceptions, in particular things like signal delivery happening during the middle of a program, or not?
That would be really nice, and
I agree.
Several projects beyond this point.
Okay.
Like being able to do this even in we control the whole universe, and we are running at EL0, knowing and just accepting that if we ever go to EL1 or EL2, that's a success because we trust the operating system and the hypervisor. Even that would be a big success at this point.
So one of the known bugs in the Morello specification is that you can disable interrupts while there are I can't remember what it's called now. They have a permission bit, which is like system privileges, and that means there's an availability problem for compartments in EL0. And I wonder if it is worth thinking a bit about availability requirements to see if we can find any other instruction set issues that should be resolved.
That sounds like a thing somebody should do. It's this style of work is really not for this problem.
Yeah.
It's very safety focused.
I mean, it seems like I would say this specific property is probably not bad, but I think generally speaking about availability is probably quite hard. So, yeah.
So
Anyway.
the frameworks that we're looking at here struggle to even stabilize this problem.
Yeah.
But,
Yeah.
And I'm sure it would be interesting to look at, but again, it's so far from.
Yeah. Thanks.
Okay, seeing none and feeling our caffeine deprivation. So coffee is, I think, upstairs in the library, if there's any left. Let's try and restart promptly in 19 minutes. I'm very sorry about that. See you soon. And thanks again.